excitation, absorption of that photon, and then we shoot it back out. And that's our emission here, the photo emission. So this is what ended up telling us that electrons have discrete energy levels that they can be in, because we see these discrete lines in the spectra that come out. And each that we see represents a change from high energy level to low energy level. So each line is kind of a key concept to keep in mind. The lines don't represent the different energy levels, but just the different allowed transitions. And all the elements are going to have a unique spectra just because of kind of the changes in the nucleus, the core charge, electronic structure. So it's a way to identify an element. So moving to the next slide, this is one thing it's really important to keep this straight, the difference between photo emission and photoelectric. So both of these involved photons, obviously, so that's why we got that photo prefix. But the photoelectric effect uses a photon to completely ionize an electron. So we produce that current, which is electricity. So that's how I like to remember it, where it's the photoelectric effect because we're making electricity, the electron fully leaves. Whereas photoemission, we're still using a photon, but we're only exciting the electron, not fully ionizing. And so that in turn results in photon emission. That emission is why we call it photoemission spectroscopy. And on the next slide, we have the Rydberg equation. So this relates back to the photoemission spectroscopy with those lines that we were talking about earlier. And it gives us all possible hydrogen emissions. So one thing it's super important to keep straight, just make sure you know which version of this you want to use, because there are two different equations which have two different constants. So if you kind of get them mixed up, you might end up using the wrong constant and get the wrong number. So here we've given it in terms of frequency and this value of R, but there's also another equation. So just make sure you know what you're using. And here N and M represent the energy levels that we're switching between. So we want to orient this so that the subtraction of the fractions will give us a positive number, right? We need to have a positive frequency. So that's why M has to be greater than N. And it gives not only all possible hydrogen emissions, but it also actually gives the exact value of the hydrogen energy levels, which is super cool. So that's something that is written here below, where these are the values of the energy levels for M and N respectively. And one more key thing about this equation is that it only works for a single electron species. So when we start looking at like helium, we couldn't use the Rydberg equation because the electron-electron repulsions just make things a little bit too complicated. So the next slide, we're talking about the Heisenberg uncertainty principle. And basically this comes from some crazy quantum mechanics math, but the gist of it is that it's impossible to know both the position and the velocity of an electron at the same time. So that's how we've kind of written it here, where our uncertainty in position, which is delta x, times our uncertainty in momentum, which is this delta p, has to be greater than some constant value. So this relates to the kinetic energy of the electron, because as we'll find out, or I guess we already have talked about kind of what the real model of the electron or the atom is. Nothing's actually moving, but the kinetic energy term that we had before is actually now confinement energy, because as we decrease delta x, so as we know more and more and more about the position, delta p has to increase, and that's an increase in momentum, and so therefore an increase in kinetic energy. And that's called the confinement energy. So next slide, this is our introduction to quantum numbers, and these are a really great way to talk about a specific electron, because kind of the key takeaway is that no two electrons can have the same 4 quantum numbers ever. So what each of these represent, N is the principal quantum number, so that's what we call the shell. L is the secondary quantum number, so that represents the angular momentum or the subshell. So this would tell us if it's in like an S or a P, that kind of idea. ML is the magnetic quantum number. So these are the spatial orientations. So for example, there are 3 separate p orbitals, like px, py, pz, because they're pointing in 3 different axes. And ML is what would tell us which one of those any electron lies in. And then MS is the spin quantum number, and really that differentiates between the 2 electrons within any one orbital, because 2 electrons are allowed to be in an orbital. So on the next slide, we have just kind of the rules for how we get these numbers. So N, like we know, is our energy level shell. It can go 1, 2, 3, way up as much as we want. L is our subshell, like I was talking about, S, P, D, F. Each one of those has a corresponding L value. So it's just a different way of saying it. L equals 0 kind of means the same thing as S. L equals 1 means the same thing as P, so on and so forth. Spatial orientation, again, that talks about which of the specific p orbitals you're talking about. So it can range from negative L up to positive L, and again, in integer steps. And then this magnetic spin is negative half or half, and that just talks about which of the two electrons, or which electron of the two electrons we're talking about. So next is the octet rule. And that's super important when we get into drawing Lewis structures and then go into VSEPR theory. It really only applies for carbon, nitrogen, oxygen, and fluorine. Technically, it also applies for neon, but really neon doesn't make any bonds, so we don't care too much about it. And really all it says is we can have 8 electrons around the atom, and that's it. Having more than these 8 electrons means we're hypervalent. That's just the term we use, and having less than 8 electrons means we're hypovalent. Just another term. And larger elements like third row elements and down, we don't use this because now we have access to the d orbitals. And then for hydrogen and helium, we actually have kind of a duet rule. Again, we don't really care about helium, but hydrogen can only ever have 2 electrons around it. Yeah, we have a question. Cyrus?
Yeah, I think you just had a couple of other questions in the chat on the quantum numbers. Okay. I just didn't, yeah.
Sorry, I should be looking at that. So, quantum numbers, yeah, no 2 electrons.
The questions that haven't been answered are, how can we determine spatial orientation from an image, and how do we determine magnetic spin?
Yeah, so spatial orientation from an image, it's a little bit like, I don't know the word, but it doesn't really matter what you call each of the specific orbitals, because you can kind of define, like, I want this axis to be the x-axis, so the one that's along this axis will be px. And if you want to have that y, well, you just turn it 90 degrees, turn it 90 degrees the other way. So you can really call them kind of whatever you want in a way. If you want to have px, py, pz, why can't elements such as sodium and magnesium have the same quantum number? So when we're talking about quantum numbers, they define electrons. So really, if we list out 4 quantum numbers, that gives us a very specific picture of a single electron. And by definition, 2 electrons can't share the same quantum number. So it's really a way of defining or describing where an electron is, and we don't really talk about quantum numbers with like whole atoms like sodium and magnesium. How do we determine magnetic spin? Again, that one's also a little bit arbitrary. You just have to make sure to remember that if one is like plus 1/2, the other one has to be minus 1/2. So long as they're opposite, that's all okay. All right, and moving into Lewis structures, this is obviously a pretty big part of what's going to be on the exam. What happens if there's more than 2 electrons in a subshell? So again, yeah, if there's more than 2 electrons in a subshell, it's a little bit arbitrary. Again, like one just has to be 1/2 and one has to be negative 1/2. But these quantum numbers are kind of the reason why we can't have 3 electrons in a certain orbital, because once you use your 1/2 and your negative 1/2, you have no more options. And so if you had another one, it would have to be that they would share quantum numbers, and that's not allowed. Getting back to Lewis structures, it's our 2D kind of representation of molecules. It's not accurate, not perfectly accurate. Cynthia's going to talk a little bit more about VSEPR theory, which is more accurate. But it's kind of our first model that we had. So I'm sure you'll have figured this out by now, but a bond we represent with a stick, just a little dash between 2 atoms, and that's 2 shared electrons. And an electron we represent with a dot, and that's actually an unshared electron. And pretty much every time you see it, they're going to be in a pair, and we call that a lone pair. So ANSBU is a super useful method in a lot of cases. If you follow that, you're not going to be able to get it wrong if you follow it correctly, I guess, if you do your math well. So A stands for available. So that's just how many valence electrons each of the atoms in your structure has. And we add that all together and that gives us A. Needed is how many we need to get every atom to its octet rule. So this actually goes to Amanda's question a little bit. And this is one of the kind of breakdowns of ANSPU, where it doesn't do well when we are talking about things that violate the octet rule. Because needed is based on getting everyone in the structure to their octet rule and not considering the fact that we might have to expand. Shared is going to be how many we need to share, and as written here, it's needed minus available. The bonds is just the shared electrons over 2 because there are 2 electrons in a shared bond. And the unbonded is everything left over. It's just the shared minus the original available that we had. And regardless of whether we're violating the octet rule or not, available valence electrons are always going to be super useful because always the available value must match the electron count that you end up with in your structure. No matter if we violate the octet rule or not, you always have to have the same number of electrons that you started with, like the available. So down here, this is kind of an equation that describes what you want to do with like an ionic charge. So if your overall structure has a charge on it, this is another kind of way to check yourself. The sum of all the electrons minus 2 times the number of bonds minus the number of unbonded electrons. Well, the only way we'd have electrons left is if there's some ionic charge. So these are a couple ways to check yourself, just counting your available, checking over all of those. And then my last slide is going to be on formal charge. So in a given covalent bond, half the electrons are kind of assigned to one, half the electrons are assigned to another. So this is the formula. I'm sure y'all have all seen it. Valence electrons minus half the bonding electrons minus the unshared electrons. The way I always remembered it was just valence electrons minus the dots around the atom minus the sticks around the atom. Kind of the like dumbed down way to think about it, I guess. And the formal charges, if you add them all up, they have to equal the sum of the total charge of the species. So the sum of all the formal charges, if you have a neutral molecule, has to be 0. If that's not true, double check your formal charges, double check your electrons, stuff like that. So yeah, that's the end of my section. We can pause for questions. Can we go over Heisenberg again? Yeah, I forgot what slide that was, but it's a couple back. So really this kind of falls out of a lot of math, and I know it's kind of hard to conceptualize for a lot of people. It's hard to conceptualize for me also, but the idea is that we can't know both the position and the velocity exactly. We have this kind of equation is trying to say that in a different way. So delta X is our like uncertainty in the position, and delta P is our uncertainty in the momentum, which is related to velocity. So in a way, this equation is just saying the first bullet point here. And this relates to the kinetic energy of the electron because as we decrease that delta X, like as we know more and more about where the electron lies, in turn, we have to go up to, like in turn, we have to have a raise in the uncertainty of the momentum. So that's going to give us like the term confinement energy we use. As delta X increases, our momentum increases, kinetic energy increases. Does that answer your question? Who was it? Okay, I'll just go on to the next one. If not, you can chat again. For an emission spectra and absorption spectra, do they match only if all the dark lines and all the colored lines match up, or can they match up? Okay, so for every atom, it's going to be unique. Every element has their own emission spectra and absorption spectra, just because of how complicated the nucleus can be, how like the electronic structure can change. So really, if 2 spectra match, they're just taken from the same element, and they better have the same lines everywhere. The only way I could like think of it is if you did one with like a super good instrument or one with like a really bad one, but I don't think that's going to be something you talk about. They should match up completely if you're going to say that they're the same spectra and the same element. Could I explain the graphs associated with photoelectron electron emission? Yeah, so that is a super important part. It's a couple of slides back here. Yeah, so I like to start in this bottom left because this is kind of one of the big takeaways. On the x-axis, we have this curly V, the frequency. The y-axis is current. And we don't see any current until we get up into this threshold frequency. So this graph is telling us that we don't eject any electrons until we have a certain energy in our photon, because frequency is directly related to energy. You could replace that if you wanted to. It's just a constant multiple. So we don't eject any electrons until we have enough energy to knock them out. And then moving on to D, as we get more and more frequency, like higher frequency, we actually don't see more electrons ejected. We just see them getting ejected faster with greater kinetic energy. Then these top two talk about intensity instead. So on the other hand, we look at intensity. As we increase the intensity, the kinetic energy is really unchanged, so long as we are ejecting electrons. However, when we look at increasing intensity, the current does increase. So that tells us that intensity is really just, since we know it's the number of photons per like unit area, unit time, that tells us that as we increase the number of photons, we're increasing the number of electrons that are ejected. And it also tells us that even though we can add as many as we want, the only way to increase the energy is to increase the frequency. So that gives us a really good picture of kind of what the light is doing and how it's interacting with the metal. All right, keep going. Is there a name for molecules with odd available electrons? How would I approach drawing the structure for those types of molecules? There is a name for it. I should probably consult with Cynthia about this, but I'm not sure you're gonna have to do any in this class.
They're called radicals, but I don't think they appear in Gen Chem for the most part.
Yeah. If you're super interested about it for whatever reason, you can email me, but you're probably not going to have to be dealing with odd available electrons. So if you do get a structure like that, like check your math, I guess. Good way to check. How would we use ANSPU for something that has an expanded octet? How would we know what to write down for the needed part? So the way I usually did it is, for expanded octets, I always first try with ANSPU and then see something has gone wrong because I don't have enough bonds to even connect everything to my structure. And then reassess, say, which ones can expand, which ones still need to follow the octet rule. So a lot of the way I used to do it is just kind of to conceptualize. I probably know what is going to expand and what isn't. And so how can I make everything else satisfy the octet rule while still keeping to the number of available electrons, making sure all my formal charges add up to the overall charge, stuff like that. So in terms of actually using ANSPU, I'm not sure there's a great way to do it, but it can definitely get you a start. It can definitely get you to a point where you realize you have to expand an octet. Is the uncertainty what leads to the arbitrary numbers for the spin and the orbit? No, the arbitrary numbers are just because there's not really a well-defined X and Y and Z in the world. We can kind of pick whatever we want to be the X-axis, whatever we want to be the Y-axis, and whatever we want to be the Z-axis. I guess a better example would be looking at some of the d orbitals because they really do have different shapes. But for the p orbitals especially, they're all the same shape. It's just a matter of which axis they lie on. So it doesn't matter so much which one we choose, just so that you know it just matters that you know there's more than one p orbital. There are actually 3 on each axis. So there are general rules for which element should go in the middle. I'd say there's a general rule, but I guess a good tip is to try and put elements with the highest valence, so the ones that make the most bonds, in the middle. So for example, carbon really wants to go in the middle, things like nitrogen probably next, oxygen probably next, and then tips, hydrogen basically always only makes one bond, so please don't put that in the middle. And halogens really like to make one bond also, so if you can avoid it, try and keep those out of the middle also. CDS video says the octet rule applies to groups, which includes that, but also, yeah, so 9 times out of 10, you are going to see things like silicon, phosphorus having 8 electrons around it, but there is the possibility that they go up. Carbon, nitrogen, oxygen, and fluorine never have more than 8 electrons around it. So if you draw one of those, it's just instantly wrong. Silicon, phosphorus can maybe sometimes get away with it, but the octet rule for them isn't really a rule. It's just kind of, they would prefer to not expand. What is the significance of wave particle duality of an electron? What does it tell us that we wouldn't be able to tell if we didn't know about the duality? Really, the idea of wave particle duality stems back to the photoelectric effect. So kind of the first thing people thought about light was this is a wave, and they were convinced that was true. And then the photoelectric effect was such a big deal because it kind of shattered that idea. We saw that as intensity increases, you would expect that you would kind of constructively interfere and increase your energy and eventually be able to ionize an electron, but that's not what we see. Intensity has no effect on the kinetic energy we actually get out of the electron. And that's kind of a classic, I guess not classic, that's a power set question I remember creating. And I know there's a key out for that. So if that's something you're struggling with, definitely look over that key. What does it tell us we wouldn't be able to tell if we didn't know about it? Really, it just was invented to explain these phenomena. The photoelectric effect is what led to the idea of wave particle duality of light. What is the significance of threshold frequency? I kind of just answered that in a way. So threshold frequency is, in a way, what told us about this. We need to get to a certain frequency of light to be able to begin ejecting electrons. And if we're under that, we can pour in like the brightest lamp we have and it won't do anything. But if we have like a tiny little one just above it, it'll still like eject electrons. So that's how I guess that's one way we knew that light was a particle, and also supports the fact that frequency is directly related to energy. As frequency increases, energy increases. And so that's one of the significant factors of the threshold frequency. What does intensity mean in the context of light? So intensity is just related to the number of photons. You can think of it as just the amount of photons that are getting shot at the metal. And it's not really a factor of frequency or wavelength or anything like that. It's just how many photons are we putting out of our light. There's no changes in the waves, just purely in the number of photons. Going back to the uncertainty principle, the smaller the space the electron is in, the larger the K. Yes, so as we constrict the electron, delta X shrinks, so delta P has to increase. Cynthia, if you could pull that up, I have no idea what slide it is on. I think you just passed it.
Oh, for Heisenberg?
Yes.
There we go.
Thank you. Yeah, so delta X times delta P has to be greater than this constant. So if we make delta X super small, we've confined the electron into a super small space. Delta P has to be huge in order to satisfy this inequality. So yeah, as the space the electron is in shrinks, the Ke has to grow because the momentum grows, and momentum is related to kinetic energy. I think my last question, do we say the octet rule applies to group 14 to 18 or group 4 to 8? I think this is actually just a question about how you're, like what periodic table you're looking at. The group, if I remember correctly, 4 to 8 in Roman numerals probably refers to the same thing as 14 to 18. But the well, okay, I guess the bigger thing is the octet rule only applies to carbon, nitrogen, oxygen, and fluorine. The rest of the group they usually stick around and try and obey it, but they don't have to. So really, like for the hard, like these always follow the rule. It's just those 4, carbon, nitrogen, oxygen, fluorine, technically neon, but it doesn't make any bonds.
Alrighty, so we'll go ahead and move on to the next little section. And so we're going to talk about isomers. So we learned that if you have, oh, my chat got really big, sorry. So we learned that if you have a compound that has the same molecular formula, but a different structure, then it's called an isomer. And there's 2 ways that this can happen. So first, we're going to see here in our structural isomers with ethanol and methoxymethane that we have different connectivities going on. So in this first one, we have an OH group here. And in the second one, there is no OH group. And instead, we have an oxygen chain to 2 carbons, which is different than what we see here. So if you have the same formula, but different connectivities, then you have a structural isomer. There's another type of isomer that can happen, which is called a geometrical isomer, which basically means that, again, you have that same formula. So when you write it out, like CH or C2, like OH6, like they both show up the same written, but then when you like draw them out, they can appear in different forms. And so with geometric isomers, basically what's happening is that you can either have like your 2 CH3 groups on the same side or opposite sides, and this comes up as cis and trans, as you see here. So cis means that they're on the same side, and trans means they're opposite sides of this double bond. Okay, we also talked about resonance structures. And so resonance structures are basically when you have, again, the same formula, now you have the same connectivities, but your electron densities are moving around. And so basically, make sure you don't get this confused with isomers. So it's like easy to get them confused, I guess, but when we're moving the location of our double bonds or moving location of bonds in general, or lone pairs, that means that it's a resonance structure. And so when you're calculating your resonance hybrids, which is basically the combination of all your resonance structures, some will contribute more than others. And we show this with like the dotted lines. So bonds that always exist are going to be straight, consistent bonds, but bonds that sometimes appear but can be moved around because our electron densities are moving around are going to be shown in these dotted lines. However, like this resonance hybrid is a weighted average of all those resonance structures that you came up with originally. And so the way that we test like which ones are going to be more shown in that resonance hybrid is by going through electronegativities and formal charges. And so in general, when you're drawing your resonance structures, make sure you're paying attention to giving the CNOFs their full octets. Like don't accidentally move an electron where it shouldn't be, where you leave like an atom hanging. Like they really want that octet, so make sure you give them that. And also don't forget to minimize your non-zero formal charges. So if it comes up where you have to have a charge, it's better again to have a smaller one. So it's better to have -1 than to have -2. So make sure you just like minimize them as much as possible. Okay, so Robert talked about our 2D structures, which were the Lewis structures, right? So we also talked about Vesper theory, which allows us to take these 2D structures and make them 3D, which is more realistic to like how these molecules exist in our world. And so this is based on our electron arrangements and the fact that these electrons want to be as far away from each other as possible because they have these repulsions going on. So yes, we talked about electron density theory, which is basically saying again that these 3D geometries are determined by the arrangement of electron domains. And they basically just want to maximize the separation between them, again, to minimize those electron repulsions that are happening. Oops, sorry. So these Lewis structures take on 3D shapes, and we're going to call them our geometries. We talked about 2 different kinds of geometries, which are our electron geometries and our molecular geometries. So when, say you're like on a test question, they ask you for the electronic geometry, that's basically asking for how many electron domains do we have around the central atom. And that can include both bonds and lone pairs. Multiple bonds count as a single electron density. So if you have a double bond, it counts as 1. And so here you see that this first row, I think you can see my cursor, this first row demonstrates our electron density. So if you have just 2, you would have linear, and then you go down the row. Then when you take into account lone pairs, that gives us our molecular geometry. And again, this happens in a pattern where we want to have those lone pairs taking up more space than the bonds. And so that like big lone pair will push our like bonds closer together. And so the angle that you saw in your electronic geometry will become smaller in your molecular geometry. I think we have a question. So the electron geometries would look like the ones on the screen right now. Yes, so the electron geometries look like this first row. And then molecular geometries are like next to this line to the right. And molecular geometries would have the lone pairs taken away. Yes, so you wouldn't draw your lone pairs on a line like this. You could either draw them like on top of your structure or just like not at all in the 3D structure, but definitely do not put them on a line like that. That's kind of weird. Well, we need to draw bond angles and polarity vectors always on our 3D structures, or will they specify when they want us to include them? I would, as a general rule, write the angles, but unless they ask for polarity, I wouldn't. But generally, when they like, based on the structure, you should know if it has polarity. And so we're actually getting to that very soon. Wait, so what's the difference between the two? Okay, so the difference between the electronic geometry and the molecular geometry is that electronic geometry includes like, it counts lone pairs as a domain. And so if you have like, I'm trying to think of an example. So if you have NH3, NH3 has 3 bonds to an H, and then it also has a lone pair. So that would be 4 electron density. So it would be a tetrahedral electronic geometry, but then because one of the electron densities is a lone pair, one lone pair tells you that you're going to have trigonal pyramidal molecular geometry. And so because of that one lone pair, these bond angles also decrease from what you would have seen in the tetrahedral. Okay, I'm getting a lot of questions. Do lone pairs on outer atoms cause angular distortion? I'm kind of confused by your question, Jesus. I don't know if you want to like raise your hand or just unmute. Okay, or we can go over it at the end. Do we need to draw lone pairs on atoms that are a part of an electron domain that includes a bond? Do we need to draw lone pairs on atoms that are a part of an electron domain that include a bond?
Better if I just explain it?
Yeah, could you explain that, please?
Okay, so like if we see on the chart here, like if we're looking at the trigonal planar one, see those X's, like if there's lone pairs on those X's, like for the one lone pair, like if one of the X's are a lone pair, but the other 2 are atoms that are bonded but have lone pairs on them, do we draw those in the geometric, I don't know, diagram or?
Oh, so you're saying if it's basically this shape, if you were, so you wouldn't be asked to draw an electronic geometry if the right geometry is a molecular geometry. So then you would just draw this bent structure without the lone pair, or attaching the lone pair right here to the E without the bond. Does that make sense?
Yeah.
Okay, awesome. Yes, so multiple bonds are shown in the electron geometry drawings. You just draw 2 lines where there is one right now. When do we draw lone pairs and when do we not? So if you're drawing 2D Lewis structures, definitely draw your lone pairs. If you're drawing these, so say this X has lone pairs associated to that atom, then yes, you're going to draw your lone pairs around it. If E has lone pairs on it, I would also draw them. I just wouldn't draw them with bonds, if that makes sense. And then when you're drawing like a molecular geometry, then you don't have to include them. I personally do include them, but not attached to a dash, because a dash indicates that there's like electrons there as well, and I think that's confusing. So like in general, you would just put, if you wanted to, the lone pairs attached to the central atom. Yes, and so electronic and molecular geometries can be the same if there are no lone pairs. So it would just be the same thing. We should draw lone pairs for 3D diagrams, right? You can, yes. How do we know where to put the lone pairs in the structure? So this is going to go back to like fulfilling that octet rule, fulfilling Ansbu. Based off of that, you know, like which electrons need lone pairs. And then Robert started answering some questions. We'll get to polarity shortly. Yeah. So Jacob, to answer your question, I would say if you know that an atom has lone pairs, draw them on, because we don't want to be like confused of whether you know that it has lone pairs on it. So in general, draw it, but don't draw them attached to a bond. That's like the main message I'm trying to say. And the angles are only affected by how many lone pairs we have on there. If you have lone pairs, you're basically squishing those bonds together and making a smaller angle than expected from the electronic geometry. Okay, my computer is messing up. Robert, I'm gonna be right back and I'm gonna try to make you host with this, okay?
All right.
Yeah.
I'll share the PowerPoint also, I guess, in the meantime. We are on this one.